Imagine achieving centimeter-level positioning accuracy without a base station, without a nearby QRS network, and without measuring relative to another receiver. At first glance, that sounds impossible because most high-accuracy GNSS techniques depend on reference stations. Yet there is a method that can achieve impressive accuracy using only a single receiver. It's called precise point positioning, or PPP. To understand PPP, we first need to look at how standard GNSS positioning works. Every GNSS satellite continuously broadcasts information about its orbit, its clock, and its navigation message. Your receiver uses this information to calculate its position, but there is a limitation. The orbit and clock information transmitted by the satellites is not perfect. Small errors remain, and when you're trying to achieve centimeter-level accuracy, those small errors become very important. This is where PPP becomes different. Instead of relying only on the broadcast information from the satellites, PPP uses highly precise orbit and clock products generated by global GNSS analysis centers. Thousands of permanent GNSS stations around the world continuously monitor satellite behavior. Their observations are processed to estimate satellite positions and clock corrections with far greater accuracy than the broadcast information. These precise products are then made available to PPP users. Think of it this way. A standard GNSS receiver uses the satellite's own estimate of where it is. PPP uses an independently computed solution generated from a global network of monitoring stations. The receiver is still observing the same satellites, but the satellite information being used is significantly more accurate. This is one of the key reasons PPP can achieve such high positioning performance. However, precise satellite products alone are not enough. PPP also relies heavily on carrier phase measurements. Unlike code measurements, carrier phase observations are extremely precise, often at the millimeter level. The challenge is that carrier phase measurements contain unknown ambiguities that must be estimated. This process takes time, and that is one reason PPP solutions do not converge instantly. PPP must also model many other error sources: atmospheric delays, satellite clock effects, tropospheric effects, antenna phase center variations, Earth rotation effects, and several other subtle influences. Each individual correction may seem small, but together they can significantly affect the final position estimate. This explains one of the most common questions about PPP. Why does PPP take longer than RTK? RTK receives corrections from a nearby reference station and can often provide centimeter accuracy within seconds. PPP works differently. Instead of canceling errors through a local reference station, it estimates and models many of those errors directly. As more observations are collected, the solution gradually improves. This period is known as convergence. The advantage is obvious. PPP can operate almost anywhere on Earth. No local base station is required. No nearby QRS network is required. Only a GNSS receiver and access to precise correction products. This makes PPP especially attractive for remote regions, offshore operations, scientific applications, and global geodetic studies. PPP is not always the fastest solution, and in many engineering projects, RTK may still be the preferred choice. But when global consistency, high accuracy, and independence from local infrastructure are important, PPP becomes an extremely powerful technique. Precise point positioning represents one of the most remarkable achievements in modern satellite geodesy. By combining precise satellite orbit information, precise satellite clock corrections, carrier phase measurements, and advanced mathematical modeling, a single GNSS receiver can achieve positioning accuracies that once required entire surveying networks. And that's what makes PPP one of the most fascinating technologies in GNSS.